Hello everyone, so now we are finally at the point where we can use all of the tools we've learned to solve a system of coupled ODEs. So here's an example. So let's say we're doing solving coupled ODEs. So as an example, let's consider the system dy1 by dt equals to 3y1 plus let's do 1y2, and dy2 by dt equals to 3y1 plus 5y2, and we want to solve for y1 of t and y2 of t. Okay, so to convert this into a form that's more understandable in the language of linear algebra, let's write in the form y prime equals to a y. As you see here, this is just a system of linear equations. Although it might look a little bit weird that we have derivatives here, these are just our output, and these are our inputs, much as like when we have a system of linear equations. So we can actually write this the following way. We can write this as y1 prime, y2 prime is equal to, just like a system of equations, right? 3, 1, 3, 5, the coefficients, times y1 and y2. And I hope you can understand that this representation here is equivalent to this up here. And just to make it obvious or more pointed out a little bit, this is our a here, this is our y, and this is our y prime vector, right? Okay, and so actually I purposely chose this system here because in order to solve a system of ODEs, we have to be able to solve for eigenvalues and eigenvectors. And this matrix here, I'm just trying to cut down the time because I know we're all very busy, but this matrix here is the exact same matrix we used in the previous video to solve for eigenvalues and eigenvectors. And for A here, I'm going to skip the steps because we'd used the exact same matrix before. We had, if you remember, lambda 1 equals 6, lambda 2 equals to 2. We also had v1 equals to 1, 3. That's our first eigenvector. And our second eigenvector, v2, was negative 1, 1. So in general, if you're given a coupled ODEs problem, you'd want to solve for the eigenvalues and eigenvectors first. But since we've already dealt with this exact same matrix, I'm just expediting the process by writing out the solution we just got in the last video. Okay, and so why you want these is because for a system of coupled linear ODEs, first order, we get the general form for a solution as follows. We get y of t, which is what we're solving for, right, is equal to c1, coefficient, times e to the lambda 1t times the eigenvector v1 plus c2 times e to the lambda 2t times the eigenvector v2. And so if we can solve for lambda 1, lambda 2 as we did, v1 and v2, we can solve for our solution. And so what this means, in our case, for our system we dealt with, is that y1 of t, y2 of t, which is the vector y of t, right? This is the exact same thing. It's just a different representation. It's the components as functions of time, which make up the vector, would equal to c1 times e to the 6t times the vector 1, 3, plus c2 e to the 2t times the vector negative 1, 1. And so, therefore, y1 of t is equal to c1 e to the 6t minus, because there's a minus here, c2 e to the 2t, and y2 of t is equal to 3c1, because there's a 3 here, e to the 6t plus c2 e to the 2t. And you may be wondering, okay, well, this isn't the complete function, right? But to solve for c1 and c2 would require us to know y1 of 0 and y2 of 0. So our initial conditions. So if we know two initial conditions, then we can substitute it into these formulas here, and we can solve for C1, C2, etc. And this also holds for like larger systems of couple ODEs, and then we just get a larger system of linear equations to solve. And we solve for C1, C2, C3, etc. And we're left with the final answer here. So that's how we solve ODEs with real eigenvalues. Now you may be wondering how we solve them when there's complex eigenvalues, and that's the case a lot of times because you have systems that are a little bit more tricky and have sinusoidals and cosines involved. So what you do in this case, I actually have a screenshot I can just copy over here. It's from a linear algebra textbook. We can follow this general form here. Okay, so let me just expand this for everybody. And I'm not going to go through an example, but it's a very similar process. So if we have complex eigenvalues, we're going to write it in the same form. I'll just explain it here. We're going to write it in the same form. This is the exact same form we used above. Y prime equals AY, but they're just using X. It's just a variable. It doesn't matter. So we write it in this form in the linear algebra language. And then we're going to get eigenvalues that are not just real numbers, but rather complex numbers. So P is the real component, and I times Q is the complex or imaginary component. So you'll get like lambda 1 equals, I don't know, like say 3 plus 2i, and lambda 2 equals, just making some stuff up here. You might see something like this if you solve for your lambda values. And so this would be your P value, and this would be your Q value. And to solve the system, you then want to solve in this way. This is the general form for when you have complex eigenvalues. You want to compute the matrix S, which contains the real and imaginary components of your eigenvectors. And you want to also take the real and imaginary components of your eigenvalues. And by taking e to the pt times this matrix product and the initial condition here, you will actually get your x of t, which will include sines and cosines. Now, I really doubt we're going to have to do this in process control, but I just wanted to have this here in case we do need to use it. So I hope this was helpful, and good luck with process control.